Problem 12 from 15.1. Says, an oscillator consists, an oscillator consists of a block attached to a spring, and it gives us the spring constant. It tells us that it's 400 newtons per meter. It says at some time t, the position measured from the equilibrium location, velocity and acceleration of the block are, so at some random time t, which we don't happen to know, we know that our position is 0.100 meters. We know that our velocity is negative 13.6 meters a second. And we know our acceleration is negative 123 meters per second squared. Okay? And so based on that, we need to find the frequency of oscillation, the mass of the block, and the amplitude of motion. All right, so I was looking at this one this morning. My first approach at trying to solve this didn't actually work, and I ended up having to do something totally different. Did some of you guys try to solve it just by using the three, position, velocity, and acceleration equations?
Yeah.
Did that work?
Eventually.
Eventually?
Yes.
With a ton of systems, and was it super, super ugly?
It was pretty ugly.
It was pretty ugly. Okay. So I do think there's a way to get that to work, especially parts A and B, but part C in particular, is that the one I'm guessing, the one that was really ugly?
That's where you just switch and do the other thing.
What's the other thing?
I don't know if it was, I didn't use energy, but it was like A equals omega squared times the position or something like that. I don't remember.
Okay. Yeah. Okay, so let's see what we can figure out here. So question A wants to know, what did I just say, the frequency of oscillation? Does it want F, like F or omega? What's the frequency of oscillation? So question A wants to know what F is. All right, so anybody come up with a way to figure that out? There's a strong relationship between these two guys. Yeah, you guys remember? So our position at time t is x max times the cosine of blah, blah, blah. When you take your derivative, the velocity at time t is negative omega times xm times the sine of blah, 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 right? When you take one more derivative, your acceleration times t is negative omega squared times xm times the cosine of blah, blah, blah. And so remember, we discovered that the acceleration at any time t is the same as negative omega squared times the position at that time. Follow? Okay, so since I have one instant at which I know both my position and my acceleration, I ought to be able to find the corresponding omega. Follow? All right, so let's do that. So let's see, that means negative omega squared is what, a over x? Did I actually write it down? So if you mathify this and solve, you will discover that omega is 35.1 radians per second. Everybody good up to there? All right, and then you can just convert radians to cycles to get your actual frequency, right? So what, divide by 2 pi?
Yeah.
Everybody good on A? Going once, twice, sold. Okay. So the answer ends up being 5.6 hertz, basically. Okay, part B wants to know the mass of the block. So, thoughts about how to find the mass of the block? Is there an equation that ties any of this together? Sure, what do you got? Adam, excuse me, sorry.
K equals M W squared.
Yeah, yep. So remember, you guys, this K, our oscillation constant, spring constant, is always m omega squared. Okay? So to do part B, so to do part B, is that green terrible? Is it okay? Everybody cool with it? So K is m omega squared. So we know our K is 400 newtons per meter. That's m times omega, which we just found to be 35.1. Don't forget to square it and solve for your m. And the m ends up being 0.325 kilograms. Is everybody good up to there? Okay. Okay, and then finally, part C wants the amplitude of motion. So,
Energy.
yeah, so my inclination was, okay, yeah. So I think probably the easiest way to do it is to use energy. Okay? I think there is a way to do it mathematically using these three equations up here, but it gets really ugly. Okay? But the idea is, as it oscillates, what should be true about the total energy, you guys? It should be constant, right? And so the idea is, at this point, I know all of this information, right? The x will allow me to find what kind of energy, you guys? The elastic potential energy. The v will allow me to find my kinetic energy, right? And when I'm at maximum amplitude, what else do we know? All of the KE is 0, right? Okay? So to do part C, here's what we're going to do. I'm going to say, all right, well, I know that the total energy at that arbitrary point T is equal to the total energy when my x is at a max, right? So that means the elastic potential energy at the given time t plus the kinetic energy at the given time t is equal to my maximum elastic potential energy, right? Follow? So you get 1/2, k is 400, x at time t is 0.1, don't forget to square it, plus 1/2 the mass we just found, it's 0.325. The velocity is 13.6, don't forget to square it. The negative doesn't matter because it's going to square out. Equals 1/2 k times x squared, and then you solve for x and you're done. Bless you. Follow? Any problems? All right. Now, I will say, if you are adamant about using the position, velocity, and acceleration equations, you can, okay? And what you basically need to do is call this a time of 0 and solve for your phase constant, and then find your maximum displacement that way. So, cool? All right. Questions on that one? All right, very good. This hits a lot of key points, you guys. So, this was good because it hit this idea about the acceleration being omega squared times the position. It hits the relationship between angular frequency and regular frequency. We used, there was one other thing that I wanted to call attention to that I lost somewhere. Oh, this. K equals m omega squared. Make sure you know that. Cool? Question?
Can you use velocity for that?
For what?
To find W?
Yeah, I guess you could. The math will get a little uglier though, because you'd have omega once here and once in here.
Well, I mean, if it's at the time, then isn't it just...
It's not the
Oh,
maximum.
right. If you make your time 0, then yeah, I guess so.
Or not even,
It's not the maximum.
not even 0, but it's like if you have it at the same time, like it's just going to be X of that time, right?
True.
Or no, it wouldn't.
No. So this is true for any time t. This is true for any time t. This is only true at the max.
Okay.
So So yeah, so you got to be careful of that. Because the velocity depends on sine, whereas the position depends on cosine. Good? All right, cool. Let's see, what was the next one we had on our list? What's this? Save.